Good morning, everyone. It's 9:10 according to my watch. I've got two different watches, one on my computer and one on my hand, and they say different things, but 9:10 is the time now. Welcome to week 3. I hope you have had a good long weekend and we're catching up and enjoying the Labor weekend, the Labor Day weekend. The fact that it was a long weekend means this week is going to be short, and so we have today, and we are on the third week of classes now. Today and Friday will be the 2 lectures we'll have this week. We are on schedule and we are doing things the way we set out to do. As I have told you, after seeing some of the feedback in the survey and some of the things that I have thought about afterwards, there might be a topic or two that I would bring forward, and we'll talk about that more. But we're on schedule, and we will have a discussion around exploratory data analysis today. Just like every day, we start off with a warm-up question, and I want to do that today too. The last time we had was a fun question, and you might have found out something about yourselves that you see what your liking is in terms of movies. But today I'm going to ask a simple question, and it's just going to be one. And this is not necessarily exactly the topic we'll cover, but I'm going to pick one word from the discussion we'll have today, and invite you to tell me. When you hear, so here's the warm-up question. When you hear the word explore, what comes to mind? You can think about whatever it is that first comes to your mind. You don't have to have the right answer, but I want to just get an idea for what explore brings to mind to you. A 1 word, 2 word, whatever it is that you would like to describe would be the warm-up question for the day. I'm going to need a volunteer to type up the warm-up question today. And let me say Magnus will write the warm-up question for the day. So Magnus, what you will do is say the warm-up question for the day is, when you hear the word explore, what comes to mind? So that those who are joining now would know what we are responding to. And I'm going to rely on our usual protocol. We will be muting ourselves, which everybody is doing a great job. Everybody is welcome, and when you are, if you feel comfortable, turn on videos. I'm going to try to use the screen to see some of you, and if things happen, then unmute yourself and you ask me questions. If not, then I would assume everything is going fine, and we will proceed in that way. I would encourage you always to make sure that we tune into the class so that you have the material as it is first delivered, and so that you get the most out of it. And some of the times, the way the lecture unfolds is going to be determined by your interaction. So make sure that you do that all the time. That you have been doing, I have been very happy with how attendance is. I understand sometimes things may not work out, so you may not be able to be attending. But we have the slides and the video recording available. The slides, I will make it a habit to post it right before class, and I have done today's. And so you'll find it on Blackboard if you go to today's date. And the way things are organized there, I think by now, everybody has become accustomed to it. The warm-up question of the day is, you hear the word explore, what comes to mind? And anything is fine. There's no correct answer for a question like this. All right, I'm going to get started. And here is a place where I would like us to see where we are and where we are headed. We completed 2 weeks, and you are very familiar with this one. Week 1, we had a discussion around what is data science as a big topic. We saw a couple of articles to read around it, and have had some in-depth discussion both on the content of the course as it in terms of syllabus, but also what data science is as a field, different landscapes. We spent last week learning R, and the survey indicated that a good number of you did not have a background in R, and for those of you who had, it will be a quick recap. This was the week that we devoted to learning about R, and we have had 2 tutorials around it. Assignment 1 is done, and so these are the things that we have completed. Assignments in general will be graded by Helen. I will interact with her, will design them in a way that would make the best learning for you. But so in general, they would be graded by her. But assignment 1, I want to grade it myself. One of the things I had thought I would do in the long weekend was to grade them and get back to you by today. I could not do that. There were many other competing things that needed to be done, and so I have not. But I promised to get back to you by Friday, and so you will get feedback on Blackboard, but we'll talk a little bit about what my general things are on assignment 1. Same way, I have looked at your the course survey, which you have completed, and some of it has, as I said, at least to the degree of reordering topics and bringing one topic forward. That one I will talk about on Friday. This is what we completed the first 2 weeks. This week, we will have exploratory data analysis as a topic covered today, and we will talk about the data science process on Friday. And these two are the things that I want to do before we go to what I call data wrangling. This is a topic for next week. The other topic that would come after it will be, according to the new ordering, I have data visualization. We could have gone either way on data visualization before data wrangling or not, but I think it would be better to have it this way. So this is where we are. 2 weeks we covered. This week is on EDA and the data science process. Next week is on data wrangling. Assignment 2, as you all know, is due on Friday, and I know some of you have started submitting. This is an assignment whose topic is exploratory data analysis. So in a way, it went a little bit ahead, and what we did last time was R. And so it does both R, introducing you to R, but it also does, as you have discovered by now, make you do some exploratory data analysis, even though we have not discussed this as a topic. And there are 2 data sets there, universities and cars. Both of these are things that you can associate with, and you don't have too much of a difficulty associating with them and appreciating the kind of exploration you would do with that data set. So they were done by choice. And there were some discussions that some of you have had, but I think in general, it seems like you are doing well, and make sure that you just submit on time. I want to remind you that Helen's office hours yesterday, some of you, if you needed, use it. But today there is 3 to 4:30. And so make sure that you use it if you have any questions on assignment 2. There was a question last time I got about Python. The language we would use for this class is primarily R, but we would accommodate Python, and especially the topics that are around machine learning would use it. And I know the majority of the class doesn't need a tutorial or an introduction to Python, but there are some who would need it. So we have decided to have one tutorial, just one tutorial on Tuesday next week, and the time is going to be 3 to 4:30, and Helen would run it, much like what the R was. But this one is going to be just one, and call it like a Python primer. And so if you need to teach yourself, you should go and do on your own, and there will be many opportunities for you to do that. But at least you will get someplace, some ideas for where to go next and things like that. And that would also be recorded and made available afterwards. This is where we're headed, and we will start discussing EDA today. Any questions before I get started? All right. So silence means always good, so I'm going to go get started with exploratory data analysis. There is a person I would like you to know when this word comes. John Taki. He is considered the father of exploratory data analysis. He lived 85 years, born in 1915, somewhere in the Northeast Massachusetts area, and passed away. He's considered the father of exploratory data analysis. He wrote a book by this name in the 1970s. He had made very many contributions. He is a statistician. He, in fact, was the first person who headed the first department of statistics at Princeton, and he did and he was at Brown for his chemistry. So he's by training a statistician, but he is also someone who has made major contributions to computer science. So those of you who have some background in signal processing may know the fast Fourier transform, or even in computer science, you might have seen that algorithm discussed. And so he is the one credited for that. So that's one of his major contributions. He spent some time at Bell Labs in much of his career, and Bell Labs is a place I would like you to know a little bit of an idea. And so he did make what is considered to be another leg for statistics, and made some of the things that are around using this one, starting from defining it. When these slides are over, at the very end, I'm going to give you a link to where you can read a little bit more about him. But if you remember, I told you what your favorite take keyword or inspired word was, and I remember at least some of you mentioned the word bit. B-I-T. He is credited for coining that term. Binary digits is what he called it when he was at Bell Labs. And he was, as I said, a lot of contributions to computer science also. And so he did come up with that name, and some people credit him also for coming up with the word software for the first time. So there is lots of things that are fun to learn about him that you would enjoy. And so there is a link at the very end of the slides that you can go to when the class is over today. So what does he say? And this is not, this is a quote from him. And I think it would bring up some of the things that I want you to know. And then this discussion would also be something that would make use of R, and I will point out to those things as the discussion goes. So exploratory data analysis is an attitude, and that's a good way to think of it that way. A state of flexibility, a willingness to look for things that we believe are not there, as well as those we believe to be there. By there and things like that, now think about data. So you've got data and you wanted to explore it. And I'm going to be very curious on what came to your mind when you hear the word explore. And EDA is a technical term now. People, when you go to interview for jobs, or you are going to talk about with, with other people, you may say this and you mean it in a technical way. So there is a notion behind it, and that's what this discussion today will show you. But when I say there, so think about data. And one of the things we do wrong most of the time is there is already something that we have in mind, and especially those of you who are in the sciences, this may resonate with you. You already have something that you think is, and you try to force the data to tell you that same thing that you were thinking. And you kind of have the lack of flexibility. All you want is a support for what you want to do. When you do exploratory data analysis, you are willing to find out things that are not, that you believe are not there, and you look for them. Some of them could be introduced by mistake, and we do make a lot of things by mistake. There are human errors, and there are times recording errors, or there are some device errors. If this thing was data that's collected by sensors, and of course there could happen something wrong about them, and so on. So that attitude, that state of flexibility, that willingness to look for things that we believe are not there, as well as the ones that we believe to be there. And I like the way he ordered them. So the ones that we don't believe necessarily to be there are the ones that I mentioned first. And of course, the ones that we believe are there. And so you come to them. This is a quote from him. I've told you enough about him. And I think it's a good way to get us started to discuss exploratory data analysis. So I started the discussion with a quote. I'm going to kind of have this discussion now by talking about the approach, what we try to accomplish when we do EDA, and we have an understanding of this one that would make us do an assignment like assignment 2, and we'll get more of them, and your projects will make you do more of that. But also, I wanted so we'll do that. The math part, the start part, the tool part will come. But I also want to talk about the approach and the philosophy behind it. So let's start with the approach. An approach for data analysis that employs a variety of techniques. And I'm going to list. If this was a class, then I would have invited you to say what you think would come out. What is it that we want to discover? That we are going to do a variety of techniques to do what? And so let me start so that you know how I am headed. And maybe I'll pause for a second and invite either through the chat, or somebody could unmute themselves and tell me. So one is to maximize insight into a data set. This will be a desirable thing to do. So we have a data set, we want to understand it, we want to know it better, and so we want to maximize our insight. If I start off this way, I think chat would probably be faster. So what would EDA, the way this roughly and informally I described with that quotation from Turkey, what would you think would enable us to do? What would EDA enable us to do? I said maximize insight into a data set. Let me see a few answers, and you can go ahead and type up what you think would come. Maximize insight, I took that. So let's see if somebody else could say something else. I'm going to wait 15 seconds. Find trends, make predictions. I'm going to have a hard time getting that one, but let's take it. Interesting patterns, explore relationships, that's a good one. Explore patterns is a very good one. Test assumptions about our data. This is going to be interesting. So pattern extraction, feeding a model. Okay, distribution, that's a good one. I'm going to wait a couple more. Every time I saw prediction, model, and so on, you might have sensed it from the way I was hesitating, but we'll get to the feature. That's a good one. Range distributions. Okay, these are all good ones. Okay. All right, so let me continue with my list. I think these are all wonderful ones. And so you will notice now what the distinction is, the things that are around models where my hesitation came, and what I am looking for here. All right, uncover underlying structure. By structure here, I mean how the distribution comes into the picture. How is there, you know, how is it distributed, right? Does it have something that looks like is a Gaussian distribution, something that has got, you know, things are around the mean in a way, and then we have, or is it completely different? That type of structure of the data. Important variables. We could use EDA to extract important variables. This one comes close to what people would call feature. We would spend some time. Feature extraction is an important thing when you do modeling. What is it, the one that would predict the most possible thing when we start talking about machine learning models to build them. So what are important variables in your data set? Some of them have got predictive values. Some of them are actually correlated, and we will talk about things to avoid having to use things that are correlated and therefore not very helpful, but important variables. And let's have a loose definition what I mean by important. This is probably a very important one. This is the place where you would find anomalies and outliers. Anomaly detection discovery is a big topic in data mining. But you could also just visually, by having to do an EDA, find out if there are anomalies, find out if there are outliers. And the difference between the two will make a distinction when the time comes. But for now, let's group them together. Things that are not behaving the way the other ones are saying. So something has stood out in a significant way. You could discover something like that. Test underlying assumptions. There was a couple answers that come close to what this one is saying. And so you've got an assumption, something that you thought would be true of the data set, and you would quickly see if that assumption is supported by the data. Develop models. This is the place where I would say we will be careful about what I mean by this one, but it is done to help us come up with a model that would be sensible based on how the data is behaving, instead of having to try out things, you know, without having an understanding of how the data looks like. So it helps us to develop models also. Now, there is, every time you have a qualifier like this, data analysis is, you know, a big topic, and so you could use it sometimes a little carelessly, but sometimes you have something that you are analyzing, and everyone would say, right, you have, you know, a subject to study or something that has happened, and so we are analyzing the data, they would say. And so there is a distinction now that I want to make, and this is the place where I want you to be careful between what John Techie was trying to differentiate and emphasize where there was not enough of an attention. So the traditional one, or the confirmatory, as it is called, or classical data analysis, would call it CDA. This concerns itself with modeling and hypothesis. So the goal of confirmatory data analysis is to say, I have got a model. This is what I think. Does my data support it? Do I have, you know, my statistical analysis on it? Then to confirm, do I have the right p statistics and things like that, that you could say, is this supported? That is confirmatory data analytics. That is classical data analysis. In exploratory data analysis, on the other hand, you do actually not have a hypothesis. You do not have a model. You are trying to see what the data is trying to tell you. Remember, I had mentioned develop a model at the very end of what you know, exploratory data analysis could tell you. That is just by looking at what you have seen and coming up with a thing that would make the most sense. That's different than saying I have come up with a model and doing a hypothesis testing to confirm that that is supported by the data. That's the huge distinction. And that's the place where much of, I know we have a couple good statistics students in, or not a couple, quite a good number in the class now. And so they would be trained. They would know what I mean by confirmatory data analysis. Much of the statistics is devoted to doing that. This one is and contrast, a place where you do not have a hypothesis, you do not have a model. And so what you are doing is our understanding, the flexibilityness, the willingness to find out things that you are not ready, that you don't believe to be there and so on. All of that means you're flexible to change your mind on how you understand the problem to be, or the one that you thought you would be solving. Okay, if you are a graduate student, this should appeal to you. It has happened so very many times to myself. So if you're lucky, if you have a mathematical problem, it's well defined, you know what it is, and you go solve it. You can either get the algorithm faster, or you made the solution more accurate, or whatever it is. But the problem is not for negotiation. You just have it. It is defined. This is what you need to solve. It's very rare that you would find something like that in the kind of thing that we deal with when it is data-driven, because your understanding of what the problem that you need to solve may change over time, depending on what you're seeing. This does not mean you just go all over the place. It's not meaning that. It just means that there is what you are after, your understanding of the problem is under evolution, and exploratory data analysis will help refine that. In fact, it may help you find the very right question to ask instead of things that you thought was the right one to ask. It may give you a clue. It may give you a clue to what would be a better question to ask if your overall goal was bigger truths or bigger reality or something that governs something. And so your initial assumption about what the problem is may change, and exploratory data analysis may help you do that as you go. All right, I'm going to make one. I trust you. This is a class that I say, if I write something, they're not going to take it very literally. And so they would be nuanced enough to know the distinction. So I'm going to make a cartoonish kind of description, separation between classical and exploratory data analysis. And I will explain what I mean when I say it is oversimplified. So classical data analysis would go like this. You've got a problem, usually something that is relatively well defined. You go collect data. If you are in social sciences, this would resonate. Even if you are in the natural sciences, this would also. You design an experiment, you collect data, and then you build a model based on that. You analyze the model and you draw conclusions. This is more like what, again, it's oversimplification, what the scientific method would tell you. You've got a problem, collect data, build a model, analyze it, conclude. This is what classical analysis looks like. In contrast, when you look at exploratory data analysis, the role of a model is reversed. And so you have the data, that's the one that you're analyzing. That's where your exploration is now coming, in the hope that it would help you determine a model. So you did not have a hypothesis. The first one had a hypothesis, you had a model, and your analysis was more to test that hypothesis. And you've got rigorous statistical methods for doing it. Whereas when you do exploratory data analysis, you haven't gone that far. You don't have anything to prove. What you do is understand the data, analyze it, know outliers, find patterns, and you would go very far. And then you can come to a point where you have a model and you try to draw conclusions. Again, this is simplistic, but at least it tells you something. And the switch between the role where a model appears and where analysis is happening is a good one, and probably not too much of yes. Thanks for the discussion there. So classical and confirmatory, now I am meaning them in the same way. So I'm going to keep my eye on the chat, but if I skip something and it is relevant for the discussion, shout out or say something, and then I'll follow along. So I don't mean to ignore, but that was right. Thanks for explaining that. Okay. I think it's enough of an approach. And so you're on the same page with me, what I mean by exploratory data analysis. So let's go talk about tools. How do you do that? What do you do to do good exploratory data analysis? You do plots, you do graphs, and you do summary statistics. Maybe that's a good summary. Maybe I don't even need to tell you more. There is a whole lot of things, and that's where John Techie would come, to do some good plots, to do some good graphs. And they will tell you a good deal about your data if you do it in a good way. If you are after what you are, trying to discover from the data. Summary statistics. This is a word that I will unpack in a moment. Is also a good way to get a general. So you've reduced a big messy data into some few numbers that would tell you a good deal about the data. That type of summary is also very important. Plots, graphs, and plots and graphs here, I mean graphs that are just plotting the data, and plots are something that you know from the tutorials we have had last time, as the term is used in R, for example. So what do you do? John, the one I quoted in the beginning, is also credited for having to come up with what are called box plots. Some of you might have done them, and I know many of you actually in your research or in whatever it is that you do them routinely. So this, if you don't know, you should know by the end of today, find out in R and find out what a box plot means and how it is defined. It tells you very quickly how things are distributed. That is a very helpful way of getting an idea for distribution of variables in your data. If you have a time series, which you have, I know there is a good portion of you who are electrical engineering students. Many of you would deal with those. If you are coming from economics or business side of things, you would also deal with time series data. And sometimes having to plot the time series data on a week basis, on a month basis, on a 24-hour basis, on whatever the scale might be, would tell you a story. You would see things when they pike up, things when they dive. Well, I don't want to talk about COVID, but if you see how things are distributed now, you see everybody on TV, and then they show you this thing is going up. Oh, that was Memorial Day weekend. Oh, here comes Labor Day weekend. And I hope you were careful, and I trust you. You're careful people, but you would know things by just plotting a time series data, and that's exploratory data. You're not building a model, you're just seeing it, and then you try to find an explanation. Electricity usage is a good example where people would say, okay, when it's a weekend and when it's normal day, or the economy, what it is doing. And so some major international event happened, and here you see the Dow Jones going deep down and things like that. So you plot, and all you've done is maybe some careful way in which you plot this, the time scale you're choosing, and trying to see whenever there is something that has happened to find a cause for it. Plots and graphs is what we're talking about. Sometimes you may find, and you probably have seen in one of the examples we've done in our tutorial one, where you have things plotted against another. You've got one thing plotted versus another, and maybe it's messy, but then if you change it into a log plot, then you get some other helpful, informative thing coming out of it. Or sometimes you may find that you can transform one variable and in a careful way. We'll see some examples during the course and then they will depict something to you that was not necessarily obvious. So this idea of having to plot, to graph, and things like that could be a lot more than what I am, putting them now just as bullet points, because you could get more out of them, right? Variable combinations, transforming them the right way, using the good time, the scale to choose. This would reveal things around it, maximize your insight to data, find anomalies, find patterns, discover important features. All of these things would come. Probably another big place where you could see what John Chucky promotes, and what you probably have already seen in your second assignment when you are invited to explore your data and come up with ways to different and things like that, is to see pairwise relationship between variables. And an excellent way to do that is something called scatter plot. If you don't know, you should know, and you should be able to use that. I'm going to show you an example of a scatter plot in this slide. This is an actual scatter plot, and an actual data set that has got to do with data. This is around blood samples of people, and if you see these names, there are some biological names, but there are some things like weight and age and height of a person and concentration of cholesterol in their blood and things like that. This is called a scatter plot. A scatter plot is where you see pairwise relationships between data sets. This is taken from the book that is one of the references I make in the syllabus. We don't use it. We'll come back every now and then when we need the Introduction to Statistical Learning with R is what the book is called. It's an excellent book. And so this is taken from there. And there are examples we will see in assignments in other places. And this is a study, I think, in South Africa and sometimes in the 70s or 80s. So this is actual. And the way a scatter plot is done is to have one variable versus another variable plotted at the same time, all of them. So in this case, we've got 1, 2, 3, 4, 5, 6, 7, 8 variables, and there is a ninth one that's just categorical, yes or no, and that's why you see it displayed this way. But let's say 7 or 8, and one thing versus another one, and on the diagonal, you've got a variable against itself, and that's why it's empty. And so you get a name for those variables, the columns in this data set. LPCA, that's some blood concentration, something around the blood, and some cholesterol level, weight, and height. And so what you see now, the way you read a scatter plot is to see, for example, the second cell in this, this first row, second column would be LPCA versus LA cobol. That's how this one is. And so you see some kind of correlation you could see. The third one would show you LPCA versus weight. And maybe it's not that nice, but there is some form of correlation, and it gets worse. There is another variable combination. That plot is just all over the place. And so this is a scatter plot that shows you one variable versus another all at the same time. When you have a data set that is manageable to get a quick view like this, do it, because you get a whole lot of information at the same time, at least visually, and it may help guide what kind of model would be good to develop. My next slide has got the same data set, but for a patient that has got some sickness, something. And so I have, you may want to study this on your own and see what the differences are. It's the same scatter plot, the same data set, when done, when something is wrong. All right.
Professor?
Yes?
Yeah. Can I ask one question, please?
Sure.
All right. So in the scatter plot, can I go back to that slide if you don't mind?
Sure.
All right. So here the two variables SVI and Gleason. So there we have categories. So do you, should we also consider those variables into our scatter plot since we only have few specified categories and that are not really giving us much useful information?
So you don't, when you do scatter plot, you do it for all of the variables. What conclusions you draw out of them, which ones you consider are important, which ones you would put in a model, which ones you want to discuss, what kind of things that you're observing is up to you. But the scatter plot would give you all the things there is in the data. And what I would probably point out here is, in this case, it was possible to have the entire scatter plot without having to leave out something, because we could view them like this. Suppose you've got something that has got 120 variables, and so you've got 120 by 120 metrics like this to plot, and that may not be helpful to visually see it. And so then you may choose to say, here is a subset of the data, the variables that I am interested in and I'm going to look, or have one way to divide them so that you could see a portion at a time. Otherwise, that kind of conclusion to draw is left for you to do afterwards. The scatter plot is just a plot of all the things at the same time, pairwise relationships. Right. When you can't do this, I encourage everybody to do it, and it will tell you, in a quick way, some very helpful things. But if you don't afford to do that, then you could do the pairwise one manually yourself, one at a time, right? For the things that you suspect would do. In fact, one of the assignment problems asks you to do that. You've got a scatter plot, wonderful. If not, then you would say, I'm going to try out this pair, this pair, this pair, this pair, and see what happens. And you could have them done one at a time. That doesn't change the idea of having to explore data in a pairwise fashion, which was one of the points there. Any other questions? All right, I'm going to go now called summary statistics, and I'm going to I'm not going to bore you by giving you a definition for what the mean is or what the standard is. I know you know these things. If you don't know, then you can look up somewhere and get them. But there is a couple points I want to make. The first one is where John, you will hear John mentioned so many times. He's a main character for us today, and rightfully so, has got this 5-point summary of a data that he advocates. because it will be useful for things that are also skewed distribution. He calls them the two extremes, minimum and maximum. You've got, data. You look at what the minimum is, you look at what the maximum is. The median, which you know what it is, and then what he calls quartiles. And quartiles are things that would tell you that, the 25% or 75% of your distribution, where they would come in. This is a good summary. This is a good summary for any data distribution, even when it is skewed. Just to give you an idea for what I mean by skewed distribution, I'm going to take this class. We've got all 70 of us and 69 participating now, including myself. And so if I was going to say, report your incomes, how much money you make, and I'm going to take the mean, I am pretty sure I'll leave myself out. I'll leave you guys as students in the class, and so that you've got kind of comparable income ranges, let's say, roughly speaking. And I take the mean. That will be a fairly good estimate for me to go by and then say, here is the mean, and that number is not going to be too much of a deviation from the average student in the class. Suppose Bill Gates decides to take this class and he enrolls, and then we've got an income that is completely skewed now. And so if I take the mean now, it becomes meaningless. You know what I mean? So that is a data in which the mean deviates from what the average thing would tell you in a class in a very significant way. But whatever the distribution is, even when it is very skewed, the minimum, the maximum, the median, and the quartiles would give you a good summary. You're not going to mislead you. And that is one of the things that you could do with exploratory data analysis. In fact, the median is what the 50 per quartile would be. And so just like the 50% quartile, you could take the 25 and the 75, and you get an idea for how it is distributed. These are numbers. And if I take, how many I had, the size, and I've got these 5 numbers, that's a very good summary. And people usually like to reduce things to just a few numbers to say what it is. Sometimes they actually like to just have one number, which is not a good thing. For those of you who have taken the network science class, we know what this means. So you've got the importance of a node. It's just a number. It has been reduced to one single thing, which is convenient, but sometimes doesn't tell you a whole lot. But sometimes, if it is done carefully, would tell you. So those 5 numbers are a good summary statistics. But we also know when things are distributed, the mean and the standard deviation tells you. These are nice to good quantities that would tell you an entire distribution. You don't even need the whole data set to describe it. I have just given you the mean and the standard deviation, and I've got a pretty good idea of what it is, when it is not skewed especially. Summary statistics is something that R is very good at, and then your exercises tell you this, and you would do this habitually, you should do, to see what it is. And so it will have more details than what I've told you now. Sometimes some of them may require you to look up some things, but that's a good way to get a summary of your statistics. I wrote identifying outliers here, not necessarily because it's a mean to show it, but more of like an outcome. So you've got the quartiles, you've got the minimum and the median and things like that. Then you have a systematic way to say when something is an outlier. And I want you to read about this yourself. When do you call something an outlier in a more systematic fashion? And John has got some suggestions for having to compute these numbers. And if it is beyond this, then we'll call it an outlier. If it is less than this, then we will call it in the normal one. So we had the approach, we had the tools, and now we had some summary statistics. And I'm going to tell you a little bit about the mindset part. So it's not just about tools, but it is also a mindset where you would want to gain intuition. You want to understand the shape of the data. The language that's written now here looks like something that is more industry driven, and it is, because I've picked up these words from the book I told you about, where you did your data science profile, by the way, where Shoot, I think is her name, was writing. And so they had a little bit of a discussion around this, and I wanted to pick up one point there, and that's why you see this. And I wanted to also come back to the place where I told you model analysis, you're closer to the data, and exploratory data analysis is your interaction with your data. You intimately want to know the data. You want to spend some time with the data itself and so on before you make a hypothesis. That's what the idea here is. And so it's also a mindset. And it's not about proving to anybody yet. That's modeling. That's hypothesis. No, that's not what you're doing now. I want to tell you, as a very quick side note, for those who want to, we are academicians for the most part now, right now, when we are taking this class and we are in this context of university, and we've got research and or we've got, this skill set that we're building. And so our, questions about exploratory data analysis now would mean, answering a research question or understanding a problem and trying to solve something around it. But exploratory data analysis for those people out there in industry is also used for things about their products, and for most of these internet companies do it. And in some ways, I'll come back and talk a little bit about this when I talk about the data science process on Friday. It's also about having to make sure that this is part of the software engineering cycle, or something that you can call it a business process, where you want to use what people are leaving behind in terms of their log, and things like that to benefit, right? And so they do it, and that's another additional place where EDA is needed, especially when it comes from logs. Now think Microsoft, think Google, think Amazon, and things, places like that. What I mean by things that are left by logs. So they would, a typical thing to do would be to understand, user behavior, customer behavior, so you have more tailored things to do for them, product recommendation and things like that. That is more on the, it's not EDA. That's when you are using the data that you're getting from people to determine models that are customized, private, more tailored for an individual. But you would do EDA also to find if there was something wrong with the browser, something wrong with the user interface that you have, and things like that. So they would make you do this. They would make you do EDS for the purpose of helping engineers or whoever are designing those things to perfect their logging processes, for example. So if you are able to appreciate what I just told you, there is a difference between having to understand the data for your own understanding and modeling later on, and using EDA as a means to quality assure or to discover things that have happened. I've told you that I have convinced myself that the visualization discussion we will have as a topic in the syllabus is going to be promoted. It's going to come forward. I've told you that. And there is a very close relationship between what you do EDA and what you do in visualization. But I wanted to make a distinction here, and I'm going to be a quick one. From the discussion we have had now, and from what you probably have already seen in your assignment too, there is visualization that you do. The scatter plot is a visualization. If I had a time series and I do it, is a visualization of sorts. But why do I have a topic called visualization separately? In fact, for some people, it's also a research area. It's a topic, a much bigger topic. And I want to make that distinction. So EDA uses a lot of visualization, but they are not the same thing. If you do EDA, don't think of it as you are doing visualization, because EDA happens in the beginning when you're trying to understand, whereas visualization is more like, now I want to communicate, especially when you want to draw somebody's attention to either you make a point, you convince them, or you draw their attention to take an action. You're persuading them. So you communicate or you persuade. That is what visualization is. So it comes towards the end, but the two have got big overlap. Part of the reason I want to bring visualization topic early, part of the reason I bring visualization early is because I want to help you, those of you who want to do a visualization for type of project, get a chance to be introduced earlier. All right. I'm going to have a table now, and we are doing well in terms of time. We've got only a couple slides to finish. This was a class. This is a place where I would ask you to raise your hands and tell me we are not in class. We are in class. Yeah, Mrs. Spock. But if you were in person, I would have made you raise your hands. But let's try to complete this table. When it is finished, we'll have entries here, and I want you to remember this and have it in your head. And when we get a chance to have a midterm or something like that, you will get a chance to reflect upon this and make sure that you have understood it. And I have listed, a few things here on this row. So CDA, is classical data analysis or confirmatory data analysis. EDA is exploratory data analysis, what we've been talking about today. And we're going to look at this, points one at a time, and then we say, how does this thing be when we are thinking about CDA? How does this thing become when we're talking about EDA? That's what we're going to be doing. Okay, chat is going to be our savior. For those of you who are brave enough and you've got something to say very quickly, and you are the kind of person who doesn't want to type, you can unmute yourself and tell me. Now, models, overused word. We use it all the time for different things, but now you know what I mean. So models is, a model, a statistical model, a machine learning model, that type of model that is related with data. If I think of models in CDA and versus EDA, what would you say? For example, the answer could be, model is a focus here, it's not a focus there, or, or something like that, right? We'll go through this. Models, CDA and EDA, what would you put under CDA? What would you put under EDA? Okay, so we've got some suggestions. Defined, not defined, more used in CDA, less in EDA, that type of thing. Okay, so I'm going to give, 15 seconds, 20 seconds for people to come up with things that you could say. When it comes to models, here is what I would put under CDA, here is what I would put under EDA. Assumed and derived, these are nice ones. Good way to differentiate them. I'll give another 5 seconds now. So 1, 2, 3, 4, 5. Okay, we're done with models. Focus. We're going to focus. What is the focus when you do CDA? What is the focus when you do EDA? This is, I know, it's not easy. So, the question is ambiguous, for lack of a better word. But let's just agree that I've got something. Okay, that's nice. The focus what is the focus in CDA? What's the focus in EDA? So every time you give an answer, you should give me a pair. So this is what I put in CDA, this is what I put under EDA, is what the idea is. So there are some hypothesis versus analysis. Okay, good. Confirmation of results versus exploration. Nice. Hypothesis versus development. Expectation versus reality. These are all very nice, very thoughtful, actually. Model versus use model versus create model. That's pretty good. All right, another 5 seconds now. We are talking about what is the focus when you do CDA, what's the focus when you do EDA. All right, the time for focus has now come to an end. Techniques, what do you say? What can you say? We've spent a lot of time talking about EDA, the techniques that are involved there. We did not spend, but we, kind of along the way, kind of in terms of contrast, talked about CDA, what techniques are. What do you say? What one word would you use for the techniques that are used for CDA? Model, graph, and so, okay, I'm going to say quantitative and graphical. Maybe it's one way. Quantitative when it is CDA and graphical when it's CDA. Rigor, data treatment, assumptions. Probably we will not necessarily have a whole lot of time, but maybe just for yourself, you could try to think up what might be a good way to come up with these ones. And so I'm going to go display them. So CDA for models, it imposes, whereas EDA does not impose. You don't make a model, you don't have a hypothesis. The focus is model when it is CDA, but as in EDA, it is data. Technique, quantitative versus graphical. Rigor, objective, numbers, hypothesis testing and things like that, very objective, whereas in EDA it's subjective, which is where you come in. This is where it doesn't mean bad, by the way, when I say subjective here. That means there is variation, but there is also an input where you can play a role. Data treatment maps to few parameters when it is CDA. That's in fact the holy grail of statistics. You want to have as few of them as possible, but in EDA you use all of the data. The assumptions in CDA is made, and your task is to prove, whereas in EDA you are not making any assumption. I think this is a nice summary that I want you to remember and say it perhaps in your own words, but also maybe exactly this way when the time comes to ask. I have 3 pointers for you to read. I encourage you to read them. They are all to some Wikipedia articles. Read about John Techie, you will enjoy. read about EDA a little bit more, and read about Bell Labs. I mentioned it, and I probably will find some other time to tell you some more things, but try to find some time during the day today when you drink coffee, read about these things, and it's a nice way to end up what we discussed today. All right, the time has come, it's 10. I know some of you have got to go to class. Anybody's got a quick question for me, too? All right. Use Helen's office hours today. If you have questions on assignment 2, make sure that you submit on time.
Someone had a question in the chat.
Sure, go ahead.
They asked if they could use Python for their homework.
Yes, you can use Python for the homework, and every time there is a tips or some hint, you would find it in the in the assignment prompt. But you're welcome to use Python. Okay. Any other questions? For homework too? Yes. So John, yes, you can use Python for homework too. Okay. I don't think there is any other questions. Hopefully I'll grade. You'll hear from me on assignment 1. Assignment 2 is what you will submit on Friday, and we'll talk about assignment 3 next time. We don't need to talk about it now. You have assignment 2 to submit. I'll see you all on Friday, okay?